go to college?
I went to Princeton, where I did a degree in operations research and financial engineering.
Fantastic. And so you've been here for a year or so, and I understand that we're soon going to be losing you because you're going to do your PhD at Berkeley.
Yes, I decided to continue my education, and I'll be pursuing a PhD starting next week, actually. I'll be studying something at the intersection of machine learning and control at Berkeley, yeah.
Fantastic. So what are your kind of main interests in machine learning?
They're quite broad, particularly because I don't have enough expertise to be to go very deep at the moment. I'm generally interested in some of the theoretical foundations that at the intersection of machine learning and control as it applies to dynamical systems. Things like how can we design dynamical systems that make use of classical control theory that is very well understood, as well as perception modules that can, with that addition, we can achieve sort of systems that can do a lot more than our current systems can do. And second, how can we both enforce and verify certain properties of the system, such as safety, reliability, and define those properties in a solid mathematical way.
Fantastic. And today you're going to be talking about UMAP, which is this new way of doing, I'm not sure if it's not that new, but doing data visualization. How did you find UMAP, and what kind of triggered you to discover it?
Yeah, I was actually working on a project a few weeks ago, in which we're trying to do clustering on physical activity data from Fitbit. And as we were exploring the data, we were looking for different ways to visualize it. So we started with the very common approaches like PCA. Then we discovered more sophisticated approaches based on neighborhood graphs that are trying to uncover local behavior in the data. And that's how I found out about UMAP. And reading the paper and delving deeper into the algorithm, I got really excited because not only it has amazing performance in practice, it also sits on top of very well-defined and solid mathematical foundation, which is something that it's kind of a theme in the things that I find particularly interesting. I do think that algorithms are so much more valuable if they have a solid theoretical backing to them.
Absolutely, and we're going to discuss this more on the call, but do you think that there is engineering utility to something like UMAP, or do you think it's something that data scientists will use interactively to understand something about data?
I think that UMAP, as opposed to other similar approaches like t-SNE, has actually a potential to be used as part of an engineering pipeline, because it can be used as a typical transform on your data, the same way you sort of scale and normalize your data with the scikit-learn transformer. You apply it to your training data set, and then you apply the same transformation to your test data set. You can do the same thing with UMAPs, because you're actually learning a metric function that embeds from the original space to a lower dimensional space. So it can be actually used as a feature extractor. That kind of application area hasn't really fully been developed yet. So there aren't as many examples in practice, but I do believe it has potential to be used in that way.
I see, because my mind was telling, my intuition was telling me that there would be some problems with the lack of robustness, or the undeterministic nature of the algorithm. But I suppose so in many ways it's not really that dissimilar to supervised algorithms. It's just a mindset thing.
Exactly. And actually something that's very interesting is that UMAP supports supervision by design. So it can do dimensionality reduction while taking advantage of the labels, and it can also be extended to sort of semi-supervised scenarios in case in which the label data is scarce.
Amazing. Okay, and just to finish off the interview, what kind of gets you out of bed in the morning?
I guess genuinely what gets me up in the morning is the desire to sort of start a new day and go to work. And I always start my mornings with a workout, and I run in the parks. And living in Seattle, where everything is so green, lush, and beautiful, I just like wake up to see the sun.
Awesome. And what's your spirit animal?
My spirit animal. Probably a tiger. I went to Princeton, and 4 years of American education indoctrination have left their mark.
That's amazing. I've been really inspired. There's a guy called Siraj Raval who kind of inspired me to start this YouTube channel, and he would go around interviewing people, asking them what their spirit animal is. So I've been inspired by Siraj. Anyway, Mahalia, thank you so much. I'm really looking forward to the paper review call.
Awesome. Thank you so much. Awesome. Hi, everyone. Thank you for joining the call, and thank you, team, for the opportunity to present. So I'll go ahead and share my slides. Okay. Let me know when you can see my screen.
Yes, we can.
Okay. Perfect. So today I will be talking about UMAP, which stands for Uniform Manifold Approximation and Projection. It is an unsupervised learning technique for dimensionality reduction, published in 2018 by Leland McInnes, John Healy, and James Melville from the Tute Institute for Mathematics and Computing. UMAP is a technique that shares some resemblance with the well-known t-SNE algorithm. The authors claim that UMAP is competitive with t-SNE in terms of visualization quality and preserves more of the global structure and produces embeddings that with an order of magnitude performance improvement. Okay. Okay, so I've structured this presentation in roughly 3 sections that will take about 20 to 30 minutes each. The general trend today is to go from applied and concrete towards theoretical and abstract. This is exactly opposite from the way the paper is structured, but I believe that for a more general ML audience, this format is better suited. So depending on your interest, you may decide to stay only for the first part or stay for the first 2 parts, or be brave enough and stick till the very end. In the first section, we will start with kind of a general overview of what the algorithm is. We will describe briefly. We will describe it briefly and compare it with other dimensionality reduction techniques. This section is intended to be fairly high level. We won't go into too much detail. We will compare UMAP in terms we will put UMAP in the language that's used in t-SNE for comparison. So if you're a practitioner and you want to have a general understanding of how UMAP works, and you want to have a couple of good reasons why you should try it, I think you should stick to this section. In the second section, we will delve more closely into the algorithm from a computational perspective, and we will explain how it works. We will describe it as a graph neighborhood approach, and you will come out of it with a more in-depth understanding of the algorithm, such that if you were to look at the source code, you'll be able to understand most of the moving pieces. And the final Y section will attempt to motivate the algorithmic choices that were made in terms of the more formal mathematical language that's used in the paper. A big sort of strong point of this paper is the very strong topological foundations that it builds upon. So while we will not fully derive the algorithm from basic mathematical principles, we will try to shine some light onto the topological foundations that it's based on. At the end of each section, I'll open the floor for questions, but either way, feel free to interrupt me, ask me any questions, and I'll try to either answer them on the spot or maybe leave them for later on if later in the slides I address your question. Okay, so with that, let's start with generally talking about dimensionality reduction, which is a very popular technique used by data scientists to look for sort of latent structure in the data. The results of dimensionality reduction can be used for visualizations, to reveal all sorts of patterns and clusters. They can also be used as a part of a pre-processing step in a larger learning pipeline. Often doing dimensionality reduction provides a certain way of regularizing the data, and it sometimes and often leads to superior performance as the number of dimensions in the data is reduced. So generally, there are all methods for dimensionality reduction fall in one of the 2 categories. They're either global methods or local methods. The global methods are the ones that try to preserve global structure and distance structure in the data with the goal of uncovering large structural patterns. The most tried and true technique is PCA, which stands for Principal Component Analysis. PCA is sort of the bread and butter of dimensionality reduction, has been around for over a century. It's fast, it's deterministic, it's linear. Being deterministic also means that the principal components are linear. Sort of the two axes in this picture are the directions of highest variance in the data. However, the fact that it's linear, it's a linear map, it puts a limit on its usefulness in complex domains such as language or images, in which the more prevalent structure is nonlinear. So here, for example, it's a prototypical example of running PCA on a toy data set, which in this case is the fashion MNIST. So yeah, and even on even PCA is able to uncover a lot of the patterns in the data because it's a pretty simple data set. Now moving towards local methods. So on the other hand, local dimensionality reduction has an opposite goal. It starts sort of from the axiom that local structure is more important than global structure, and it has as a goal to prioritize fidelity to local geometry as opposed to preserving distances across structure on a global level. So the prototypical technique for local methods is t-SNE, which stands for T-distributed stochastic neighbor embedding. This algorithm is great at capturing nonlinear behavior in high-dimensional data. So meaning that if 2 points are close, so meaning if the 2 points are close together in a high-dimensional space, then they have a high probability of being close together in the embedded space.
Okay.
Sorry, was there a question?
So rather than having DOS?
I'm sorry?
I think that was someone who needed to mute, but could I ask a quick question?
Of course.
So fashion MNIST, because MNIST was always the canonical kind of, basic image classification data set. And, when did fashion MNIST come into play? What's the difference?
I think it came into play, it's one of the Zalando data sets. It came into play maybe about 7-8 years ago when pretty much all algorithms were given perfect accuracy on regular MNIST. So people looked for some easy drop-in replacement for MNIST for benchmarking, and that was the origin of fashion MNIST. It contains images of fashion items and has exactly the same size as a regular MNIST, making it a very easy drop-in replacement, but it has a slightly more complex structure. For today's sort of day and age machine learning, it's equally sort of toy data set for most machine learning algorithms. But it for here just serves as an illustration purpose of how the algorithm works. Okay,
so it has a lot more diversity in terms of the different images, but it's still kind of center aligned and there's a white background. And okay, right. It's
still very regular as an image, so it's no wonder that it's behaving well in this scenario. Okay, any other questions? All right, we'll continue that.
Well, in these images that you're showing, what would the perfect dimensionality reduction look like? What would absolute God's algorithm, what kind of image would it produce in this sort of 2D projection space that you're showing here?
It's actually a very hard question to answer because here we're sort of overlaying the class labels on top. So this is the way it runs here. It's a purely unsupervised technique. So if you ideally what you would want to have is you'd want your data and your embedding to learn. You'd want to learn an embedding from the data such that it's able to perfectly separate all the labels without actually having access to the labels, such that sort of the labels are intrinsic to the data, and the algorithm that embeds this data is somehow magically able to uncover that. and you also, that's kind of giving you this local structure, and then you'd also want to like recover some of the global structure. Maybe you know that all the shoes are kind of similar to each other, so you want them to be kind of in one place of the embedding, and all the shoes are very different from all the trousers, so you want the trousers and the shoes to be in different areas of the embedding. So that would be sort of ideal.
So like a perfect image here would just be however many categories there are, it looks like about 10 or whatever, would just be 10 little colored circles that were well separated from each other.
Actually, you wouldn't necessarily want to have a circle, because maybe the sort of the data that corresponds to different images in that class might have some interesting geometrical structure in this multidimensional space, and you'd want to somehow recover that. Maybe like imagine the data circle is sitting on some like multi-dimensional circle or whatever. And you want
you definitely want a lot of white space between the colors. You want them well separated. Is that right?
It depends on whether you want to use this dimensionality reduction further on as a sort of pre-processing step for clustering or for other algorithms. For visualization, arguably even something like t-SNE, which shows the fact that that images or samples from the high dimensional space that are similar to each other end up clustered in similar areas of the embedding, is kind of good enough for visualization purposes.
Okay, but we can agree that overlap would be bad, right?
Yeah.
Overlap would be classification error. Okay.
Except here, there's no classification yet.
One of the things that seems to be relevant in UMAP is the macro distances, the global distances are also relevant. So you can actually tell a lot just by how the clusters are related to each other in space. How does that contrast with t-SNE? Actually,
it's a great question, and that it will be actually answered on the next slide, so maybe I can continue with this. Thanks for asking that. Yeah, so just kind of finishing up the t-SNE discussion. So here it's again t-SNE on the fashion MNIST. So we can definitely see this sort of clustering behavior. But the one that we compare t-SNE with PCA, there's a few things that are sort of useful to mention. First, it's generally much slower. Doing embeddings in dimensions higher than 2 is computationally impractical. So that's why t-SNE is mostly limited to visualizations. It's not a deterministic technique, so every subsequent run returns a slightly different projection. And the visual output is highly dependent on the choice of hyperparameters. And the other thing that's really noteworthy for all the local methods is this axes in which of the embedding space are not meaningful in any way. The x-axis and the y-axis have nothing of the sort of highest degree of variation or anything like that PCA has. So from an interpretability standpoint, the local methods lose a lot of that structure. So now let's actually jump into UMAP, and I'll address your question. So UMAP is sort of the new kid on the dimensionality reduction block. It stands for Uniform Manifold Approximation and Projection. So from a practitioner's standpoint, it's very similar to t-SNE. If you haven't really worked very much with local methods, you might look at this and not really have a hard time telling apart UMAP from t-SNE visualizations. So something that we will talk a bit maybe in the next few slides is what Tim already foreshadowed, is the fact that UMAP, while being a local method, has the property of preserving global distances. In practice, it's much faster and more robust than t-SNE, and what we will talk towards the end of the call is the fact that it builds on top of solid mathematical theory. And here we have UMAP on fashion MNIST. So let's first kind of, actually maybe I'll skip over this and I'll return back in a second. I think it's probably better to just do a comparison between UMAP and t-SNE. So UMAP has some significant advantages over t-SNE, aside from the computational advantages that we'll talk about later. So what we were talking about earlier is that it captures global structure better than t-SNE. And because t-SNE is limited to a two-dimensional space, and completely loses any sense of local or global distance, it cannot really be used as a general purpose dimensionality reduction technique, whereas UMAP makes a good case for why it could be used. So here, let's actually look at an example. So here we have, we can see how similarity is being preserved across visualizations. So here I've highlighted the shoes in the data set. So arguably, the shoes in the data set have sort of similar global structure. So we can see this in the PCA. They're kind of bunching together here on the lower left. We can see that t-SNE is able to kind of preserve this local behavior as the clusters corresponding to ankle boots, sneakers, and sandals are sort of in one space. However, UMAP not only does the same by keeping sort of the shoes together, moreover, UMAP is able to differentiate between shoes and other classes by kind of pulling that cluster apart from the rest of the projection.
Sorry, Mihaela, can you just point out which one is UMAP and which one is t-SNE?
Yeah, my bad. That's what I was saying. They look sort of fairly similar. So the top one is UMAP. The bottom left is PCA and the bottom right is t-SNE. So t-SNE technically a good way to kind of see which one is a t-SNE plot is if the more uniform it looks, the more sort of equally spread out the clusters are in space, the more likely it is that it's a t-SNE plot. Okay. Any other questions?
Yeah, quick question. Could you speak to, because it's not a deterministic algorithm, is it? So, I mean, we'll get into this a little bit more later, but in an engineering context, we would like to be able to have something which is robust as possible and produces similar results every single time because we might not be interactively supervising it. So if you ran, you see we've got the UMAP on fashion MNIST in the top. I mean, if we ran that 10 times, what would it look like? How would it be different every time?
So what would be different every time? It would be different up to uniform scaling and rotation. So you would get the same, almost the same projection, except that it could be rotated and scaled because the absolute value of the embedding numbers has no meaning. So it's equivalent up to scaling and rotation.
So does that mean that if I took two items in the embedded space and took the cosine distance on 10 different UMAP projections, they would be pretty similar or normally distributed?
So if you were to take two vectors and the projected space for different runs, they would stay constant. With some slight caveat because there's some extra random parts of this algorithm, but for most part, yes.
And that's assuming that the algorithm is robust, so there would be slight perturbations or changes that could make it completely different, but most of the time it would be the same.
Yeah, it will be almost always the same. The only source of randomness would come from the algorithm that finds the approximate nearest neighbors of a point, which is typically a pretty low source of randomness.
Cool.
And what about what quantitative methods or rather metrics are used to score performance within this kind of just unsupervised structure determination? So like if I'm looking at PCA, I like it because I can almost have like I can just have angles defined from sort of that little phantom point of origin there. That's a very simple measure that can discriminate kind of the categories with a little bit of extra work there on that, green section. Whereas like the borders for the other ones are much more complicated. So what sort of measures are there of sort of the simplicity of the, the structures that are created?
So unfortunately, there aren't any metrics for comparing visualization quality. It's very sort of hand wavy. The arguments that I will be giving will be very hand wavy in terms of, this looks more separate, this looks more this, more that. One way to compare them might be to use the embeddings for a future task. For example, you could run clustering on top of embeddings and then compare sort of internal validity metrics for clustering for different types of embeddings and then compare that, but there isn't necessarily a method or a well-defined metric that would compare between two different visualizations.
So that could be your thesis topic then, right?
Who knows? Maybe, perhaps. It's definitely something worth looking into, especially when we are trying to use these techniques in a more kind of streamlined engineering fashion.
Can I ask one more question? Sorry.
Yes, of course.
So you said that in t-SNE, the axes don't have an interpretation. In UMAP, is there an interpretation for the axes?
No, they still don't have an interpretation. What I mean here by preserving global distances is that things that are far away in original space tend to be pushed farther away in embedded space. The axes are still not meaningful. It's just the projections kind of preserve some notion of the global distance. But it's by intent, sort of very non-formal language here. Okay.
Could I just ask one more quick question? If we were to do some sort of interpretability study for UMAP, what would that look like? Because we have LIME, for example, for looking at classifiers, and that does counterfactual examples and data grouping. What would it look like in UMAP?
Well, I mean, that sort of relies on labels. This is intended to be a unsupervised learning technique.
Oh, I see. But you're right. But what happens if we did? You see here, we've actually applied labels retrospectively. Would it then make sense to do some sort of interpretability study?
I don't see why it wouldn't make sense, but I don't think that I can think of a way to do it on top of my head, to be honest.
Okay. I mean, for example, you've labeled the cluster here, which are the shoes.
Right.
So that seems to be somewhat relevant in this projected space. How much of a shoe is it?
Right. Yeah, but as we will see later, the way this embedding is computed is it's a collection of highly convoluted nonlinear maps. So I think what's really hard here is to say, do I go from point X to point Xi in my embedded space by moving how much to how much in my original space? You could do that at a local level because it preserves locality. You could say, if I move in a certain neighborhood in my sort of original high dimensional space, then I'm sort of guaranteed to be in a similar space in the embedded space because of the construction of the algorithm. But I don't think you can have sort of a kind of a differentiable thing that will tell you sort of by moving this thing, by moving this quantity this much, we will get in this place of the projected space. But I think it would be interesting to explore. I'm sure there's probably variants and sort of ways to parameterize this this approach in which we can probably uncover some of that complexity.
Cool. Thanks a lot.
Okay. So now actually let's kind of go on, just continue the same train of thought. Let's look at dissimilarities. So when looking at dissimilarities, UMAP sort of has a much better behavior than t-SNE. So for example, when we look at bags and trousers, they're very different in the PCA, meaning that they have very different global structures. However, t-SNE sort of puts them actually really close to each other, whereas UMAP is able to kind of pull them farther away in the embedded space. So this is what we mean by preserving the sense of the global structure. Okay, now actually let's go back at actually briefly describing the algorithm by putting it in the language of UMAP. So as a kind of a very high level sketch, the way all of these local methods work is first by in a two-step approach. First, we want to identify a similarity structure between points in high dimensional space. And then we want to embed this point into a lower dimensional Euclidean space, such that this similarity structure that we've derived in the first part of the algorithm is preserved in the lower dimensional embedding. So for t-SNE, what it does, it computes a a quantity, a similarity quantity condition. So Vj conditioned on I. It's essentially for a point j, we're computing this this quantity which is derived from a normal distribution, and sigma I is just a normalizing constant. Then we transform this similarity metric into a probability by averaging it out over all the similarities, and then we do another normalization step such that as we sum, so we do a symmetrization step. So here's the conditional probability, and now we sum it up such that we can make it into a regular probability. So probability that it defines sort of the strength of the connection between 2 points in the original space. For UMAP, we have something very similar, except that here we have a bit of a difference. So instead of taking an exponential with respect to the two norm distance between 2 points in high dimensional space, we can support any distance metric. For example, cosine similarity, or Manhattan distance, or anything like that. With a caveat here that, or with a, I guess with something else here. So it's not, we don't take the exponential of the negative distance, but we take the exponential of the negative distance minus the distance to the nearest neighbor. Oh, I actually have a mistake here. I should have another parenthesis. So essentially, we are judging similarities between points in high dimensional space as they go from the as they compare the distance to the nearest neighbor of that space. Then we perform a symmetrization step in which we take sort of the similarity of j and I from I perspective, then we plot the similarity of I to j from j perspective, and we subtract their product. So probabilistically, if you think about it, this is the probability that the edge between I and j exists, which is the sum of probabilities minus the product probability. So kind of there's a probabilistic intuition here as well. So that's how we get getting the probability structure gives us this this sort of the result of step number 1. And then step number 2 is to embed in a lower dimensional space. So for the lower dimensional space, for points xi and xj in let's say in a 2D space, we define sort of this similarity as a student t distribution, which is where t-SNE gets its name. Then we normalize over all of these such that they sum up to 1, and then we're trying to maximize the to minimize the KL divergence between the two distributions. So we have the Pij, which is the distributions of probabilities across the original high dimensional state. Then we have Qij, is the distribution of probabilities over the new embedded space, and we iteratively sort of change the location of the points in the embedded space until these two distributions sort of match up. So that's what the KL divergence does. When we compare to UMAP, here is we have a slightly different way of assigning similarities between points in embedded space. So if you look here, there's an A and a 2B here. We'll explain later what their goal is, but it's actually very similar to t-SNE, because if you were to replace A and B by 1, you'd actually get the t distribution that t-SNE uses. What is different here, and this actually highlights a bit of why UMAP preserved this global structure, instead of minimizing KL divergence, here we're actually trying to minimize cross entropy. So we have this term, this first term of the UMAP. It's actually very, very similar to the term used by t-SNE. Mind the slight different sort of definitions of Vij, but both Vij and Pij are kind of definitions of similarity in the original space, and Wij and Qij are definitions of similarity in the embedded space. However, so this term is very similar to what t-SNE has. and the term on the right in the cost function is kind of a reason why t-SNE gets its global structure. So this can be sort of labeled, the first term could be labeled like sort of get the clumps right, put the points that are similar together, and this can be labeled as if points are very dissimilar, make sure they are pushed farther away in the embedding. So this is a very kind of hand-wavy explanation. But at a high level, both UMAP and t-SNE work in similar ways. So we were talking about earlier about sort of embedding stability. So one way to compare embedding stability is to take embeddings, take an embedding and then perform iteratively embeddings on subsamples of the data. So here we have the.
I'm sorry. Can I just interrupt with a question back to that mathematical definition? Can you just point out why because I believe you said that t-SNE has much slower computational performance. Is that correct?
Mm-hmm. Yes.
Can you point out what in those equations makes the big computational difference?
I think is it not the LSH? So it does approximate nearest neighbor, and it does hashing on the points. So it doesn't need to do an n squared. Is that right?
Exactly. Yeah. So t-SNE is an n squared algorithm because at every iterative step we have to renormalize this for all the n points. We have to perform the steps. Whereas in UMAP, when we compute similarities, and we only compute similarities for the k. Oh my God, sorry. For the k nearest neighbors.
Okay.
So the algorithm scales sort of with number of neighbors as opposed to squared of the dimension of the data set.
And those k nearest neighbors are still fast to find, even in a complicated high dimensional space.
So we'll talk about this later when we talk about implementation details, but UMAP uses approximate nearest neighbor, which is an algorithm that's based on random projection trees and nearest neighbor descent, and it has an empirical performance that scales as n to power 1.14, I believe. So it definitely is subquadratic. Yeah.
Cool.
Quick question on the formula. So how do we like Vij? Is there an intuition for like why it's guaranteed to be less than 1? If assuming it's a probability.
For t-SNE or
for UMAP.
Okay,
like
so
Vij equal to Vj given I plus Vi given j, the formula on the right side.
This one. Okay, so if you think about it, it's this is if you have from a probabilistic perspective, a probability that if you have two binomial events, probability that either A happens or either B happens is the sum of the probabilities minus the product of the probabilities. So
well,
if you have two,
can I jump in? It's just because d of xi xj is by definition always larger, excuse me, than rho I, because rho I is the distance to the nearest neighbor.
Yeah.
No, I'm talking about the one after
the bottom. Yeah, the bottom. So you think about it from a two coins perspective. So this is probability that one coin turns up to 1, and the probability that the other coin turns up to 1. So the probability that at least you'll have one coin that's gonna turn up to be heads is the probability that both of them will turn up to heads individually, minus the joint probability that they will both turn up being heads.
Sure.
So that's and also you can just if you have two numbers between 0 and 1 and you take the sum minus the product, you can very easily mathematically sort of show that between 0 and 1. So it can be interpreted as a probability.
Cool.
Yeah. Okay. In the interest of time, maybe we can start jumping over to embedding stability. So here in this data set, we use the cytometry flow dataset, which is a well-known dataset in bioinformatics. So on the right, we have the t-SNE embedding, and on the left, we have the UMAP embedding. In blue, we have the original embedding on the full dataset, and in red, we have the embedding of a subsample of the dataset. So what we can see is that for most part, the red and the blue kind of match for UMAP, whereas for t-SNE, it's a larger departure from the original embedding. So how do we sort of compute this this embedding stability number? We compute something known as the Projection distance. So what this is sort of the minimum, assuming we find the optimal rotation and uniform scaling of both projections, then we compare, once we do this, we compare the L2 distance between each point in the embedded projection. So what we can see is something that UMAP produces stable embeddings even at only 5% subsampling rate. So even when we sample sort of very little here on the let me know if you can see my mouse here on the left side of the graph, we still almost get the same embedding. As we go sort of farther and farther along, when we subsample more and more of the data, we get almost sort of perfect embedding each run up to uniform scaling and rotation. Whereas t-SNE sort of even at full subsample size, at full data set size, sort of consistently produces different embeddings. And we will see why this is when we'll talk about how UMAP initializes its embedding process. Okay.
Could I just ask a quick question? Is stability the same as robustness for all intents and purposes, or do you see them as being separate?
I guess depends. I would say robustness is a bit different. Typically I would think of robustness as robustness to noise, as if you were to sort of perturb the data and add noise to it, would the resulting embedding be comparable or similar, and then measure distance to that.
I see. So in this one you just showed, there were no perturbations whatsoever. We just run the algorithm lots and lots of times, and then we just look at the distances between the points.
Yes, lots of times on subsamples of the data. So we run once on the 100% of the data, and then we run on like a random 5%. So even that 5% already encodes the geometrical structure of the data, and UMAP is able to recover that geometrical structure regardless of whether it uses the full data set or a smaller subsample.
Cool.
Okay. So different sort of comparison between t-SNE and UMAP is the scaling with embedding dimension. So this is a very small data set because anything bigger and t-SNE cannot handle more than 2 dimensions. So we can see here that sort of UMAP on the bottom in blue scales linearly, and the slope is almost imperceptible, whereas t-SNE just blows up with the embedded dimension. And this is one of the many reasons why t-SNE has not been used as a more general dimensionality reduction, because anything beyond sort of 2-3 dimensions is computationally unfeasible, whereas UMAP scales very nicely with dimension.
Could I just ask why? Because I thought the quadratic term on UMAP was a function of the number of examples, not the number of attributes. So why does it blow up with attributes?
So the reason so what's different is how UMAP and how t-SNE optimize their embedding. Once they have sort of the similarity computed, how do they optimize for it? t-SNE uses some sort of quad trees approach that doesn't scale very well with the dimension of the embedding. I'm not very familiar with the inner workings of the algorithm for t-SNE, but for UMAP, it's based on stochastic gradient descent and negative sampling, which performs sort of equally well regardless of or almost equally well regardless of the embedding dimension.
Cool. And why is UMAP more stable?
UMAP, I think largely it's because of the way the initial embedding is initialized. So oh my God, my battery is running low. Hopefully my computer doesn't die in the meeting. t-SNE, there's many variants of t-SNE. So a lot of this are optimized and run on GPUs and have sort of different. It's been around for like over 10 years. Generally, it initializes the algorithm by putting the points sort of randomly in the space, whereas UMAP starts with a spectral embedding as the initialization of of the embedding, which has some very nice properties and helps the algorithm be more stable as it improves that, as it iteratively modifies that embedding.
Cool.
Okay. So similarly, with varying some sample of the data set, the UMAP scales a lot better than t-SNE, even sort of highly optimized, sort of like 8-core t-SNE that run sort of optimized C code. Even with that, t-SNE overperforms in terms of number of data points. And also it scales much better in terms of the ambient dimension, as in sort of number of features in the data set. So here's a log-log comparison between UMAP and t-SNE, and here we can see that we are able to sort of embed things that are have very large ambient dimension. And as an example, this is a super cool image in which they took 30 million integers, and they featurized this as a matrix of 30 million by 1.8 million, such that every integer has a corresponding a prime factorization vector. And then you take that prime factorization vector and just shove it in as raw data into UMAP. It takes about a few days, and then you obtain this like amazing visualization that shows every single integer mapped by UMAP, and you have all this like really cool clouds of points and stars, and there's a kind of a quest.
Do you have this available as a poster that we can order?
Yeah, actually, it is. There's a blog somewhere someone made it, and I found it as I was googling up different applications of UMAP, and lo and behold, I found this, and they have like large posters, and they have sort of different ways in which it's colored, so you can look at sort of numbers that are colored by whether they're prime or not. There's a kind of a different pattern you observe, and you color the numbers whether or not they're like, have different other special properties, and then you sort of like end up having this very
Tim, I'm thinking like, coffee mugs, T-shirts. You need to sell this channel, raise money.
Yeah, well, in grad school, figure out a way to pay for it. Yeah,
amazing.
Okay, so in the interest of time, I'm just quickly going to go over different applications. So overall,
oh, I think Mahela's battery might have just run out, so let's just give her a couple of minutes. But yeah, this is absolutely fascinating, isn't it?
Yeah, I'm kind of curious how, because she mentioned the algorithm for the nearest neighbor thing was 1 or to the 1.14. So I'm wondering like how much of this slowness of some of these others is just quality of implementation issues, like if there are just faster algorithms for pieces of it or approximations.
I think there's
t-SNE well optimized. Sorry, Tim. Sorry to cut you off.
Oh no, go for it, Justin.
Yeah, t-SNE is well optimized. It's just a core fundamental n-squared algorithm approach to it. So that's the core.
I was wondering if there's like because people thought matrix multiplication would never get any faster, and they keep finding faster ways. I'm just curious about that, whether there's a trick. I guess.
So the trick with UMAP is that this thing called local sensitive hashing, and that's a really, really good thing when you have these quadratic problems and you want to do nearest neighbor or approximate nearest neighbor. You do one pass through the data and you come up with this kind of hashing function for every single vector, and that reduces the dimensionality, and it means that you can very, very easily, for a given example, see which ones are in the neighborhood without having to do that quadratic search. So I think that's the reason why the time complexity is lower. But Mahela was also implying that there's that second stage to the algorithm. So after you do the initial embedding, you solve this optimization problem that does the KL divergence in the case of t-SNE. I think that obviously has this quadratic term as well, and I don't think that can be improved with LSH.
Oh, hello. So sorry, my computer just died in the middle of the presentation.
That's okay.
All right, awesome. Hopefully I have an issue with my charger that it doesn't charge when I'm plugging into a projector. So let's see.
No problem. No problem. Yeah,
Okay,
we were having a philosophical digression.
Fantastic. Okay, let me know if you can see my.
Yes. Yeah, we've got it.
Okay, so typically so far in the past year since it's been developed, UMAP has seen a lot of usage as a visualization tool because it has been designed to be just a drop-in replacement for t-SNE. So a lot of places that were using t-SNE before just have gone with UMAP. So a big area of application is bioinformatics. Empirically, researchers have found that it leads to it producing equivalent local structure but superior global structures. Here's an example of running UMAP on single cell RNA, which is a pretty large data set, very high dimensional with a lot of interesting latent structure. Other really cool project is visualizing word-to-vec embeddings, which is again a very large data set. And here's a really cool link that shows how this is done. Let me try to
and that looks so much better because I did a call on the skipgram model and I showed the t-SNE visualization of just 10K words, and it didn't look anywhere near as good as that. There was a cluster for the first names, but other than that, it was very homogeneous.
So here is this thing called an embedding projector from TensorFlow.
Yeah,
so
that was what
if you Oh, awesome. Yeah. So here we can see in UMAP how, like, if you look for the word Microsoft and their neighbors, they sort of cluster very nicely in this 3D UMAP representation. So giving us sort of some confidence that word2vec is picking up some interesting sort of patterns.
So they must have just added this, because when I did the paper call 2 months ago or something, this wasn't there. They've just added it.
Interesting.
So yeah, super cool.
Just a quick question. In terms of the implementation, do you have any suggestion in terms of like the parallel or even better distributed implementation of this algorithm? Because like t-SNE was not really, it was poorly developed in terms of the parallel implementations.
Yeah, so nothing that's done here is so the algorithm is very amendable towards being parallelized and being distributed. So for example, when you build this similarity scores between points, there's no reason you cannot optimize this. Then since it's very local, you can take sort of different neighborhoods of k neighbors and optimize the layout for them. But the current implementation is actually doesn't make use of any distributed computation, nor does it make use of any sort of advanced languages for numerical computation like C or C++ or anything. It's all done in plain Python, and even with that, it overperforms the more optimized versions of t-SNE.
Cool, thanks.
Okay, and another really cool application area is this thing called Activation Atlas that came a few weeks ago from DistillPub. What it does is it takes feature inversions of millions of activations from an image classification network, and then it runs UMAP on top of the inverted features. So it kind of creates this tool of exploring the space of activation of a convolutional network. So let me show you how this looks on. So if we look here.
And can I just say, this paper is one, it's on Distill, so I'm not sure if you call it a paper, but if anyone wants to do a paper review call on this, please let me know, because this is super, super cool.
So essentially, let's say if we're looking at some label, let's say we're looking at a type of dog, and we look at different layers of the network, and we see how the activation maps are topologically placed close to each other. And UMAP is used for visualization for finding similarities between topological similarities between activation maps of different images. So as we look at different layers, we can see how different layers learn different types of features. So towards like the end of the network, the features look more and more like dogs, and towards the beginning of the network, the features that get activated look more and more like just patterns and more low-level features. So it's a really cool tool for just like visualizing the data, and it's really worth giving it a read. The way UMAP is used here is just for clustering together the space of activations. Yeah, okay, so with that in mind, let's jump back to the presentation. Okay. So another area of application that we've sort of hinted towards is that UMAP could be used as a general feature extractor. It could behave as a standard sklearn transform. So
We lose again.
I'm sorry.
Oh, sorry, Mahela, we lost you for a minute there.
Hello? Yeah, so let me get back to the slide from the beginning. So another way of, hello? I'm having very poor network quality.
Yeah, we've got you back now. We lost you just for a minute.
Okay, no worries. So as application areas, another area could be using it as a feature extractor. It can behave as a standard sklearn transform in which you learn a transformational train set, then you apply it to a test set. And thus, it actually learns a metric for transforming the original high-dimensional space, a nonlinear transformation, to a lower dimensional space, which is something that t-SNE does not do. Because it learns this metric, it can be a viable alternative for metric learning. And currently, the only sort of methods used for metric learning is like CMEs and triplet networks. So this could be an alternative for using. So here we can see in the image how we've trained UMAP on 80% of the data, and then we've applied this transformation to the other 20%, and we can see how the embeddings are fairly consistent across the train and test sets. Okay. So this kind of concludes the first half of the presentation, which was more of a visualization and application first part of the presentation.
Could I just ask a quick question? I know when we did the warm-up call, I asked this as well, but we had Devon Yelm on a few weeks ago from Microsoft Research, and he was talking about Deep InfoMax, which is a kind of self-supervised, it's an unsupervised algorithm for coming up with powerful image embeddings, and it does so by looking at lots of kind of self-supervised tasks and generating a powerful representation. But I'm assuming the reason that works is because it's still using convolutional neural networks, and it's parameter efficient, and it's location invariant and so on. My assumption is that if you used UMAP directly on high dimensional images, it wouldn't work in the same sense that it would work on a structured data set, because images have all of these kind of properties in terms of local dependencies between pixels and so on. So would you first use a CNN encoder and then use UMAP, or do you believe you could just use it directly?
I think both could be valid approaches, because you could argue that even for complex images, you don't need, hundreds of dimensions to encode what a natural image looks like. So doing some level of sort of lower dimensional embedding, even on original space, could prove useful. What I believe more is that when adding on top of raw features convolutional layers, they sort of are able to encode this property, sort of explicitly encode these properties that we know images have, such as like translational invariancy and stuff like that. So if we have a first step of us sort of doing a kind of an autoencoder approach, or just running a network and learning a bunch of embeddings, we can argue those embeddings sort of lie on some interesting sort of topological space, and then we can run UMAP on top of those embeddings. So what we've seen in the distal paper is running a UMAP on top of activation maps. We could as well run it on sort of CNN feature maps that are somewhere down a network. So I think that could be very interesting. I haven't seen it, but I do believe it could have an interesting application. Yeah.
So if I understood kind of the UMAP algorithm correctly, for example, if an image has a feature that's, I don't know, whatever, a triangle inside of a circle or something, and it can appear at multiple locations in the image, it can be translated all over the place. UMAP would need, multiple clusters. It would need multiple sort of clusters to identify that shape in different locations. So I think that would kind of be like the fundamental problem, right?
Actually, no, that wouldn't be a problem because for every point, when you're trying to find their k nearest neighbors, they are the same regardless of whether the image is translated or not, because the distance between 2 points would be the same. And if you sort of magnify...
I don't think that's right. I mean, because if something's in the upper
maybe
right,
I'm not understanding you. I'm sorry.
Yeah, so if I have a circle if I have a triangle and a circle in the upper left of the image, that's going to be at dimensions, whatever, 0 through 600 or something. And if it's the bottom right, it's going to be dimensions, 1440 through something another. So they're going to be very far apart. They're not going to be nearest neighbors in that dimensional space. So
I believe there would be near. So you're saying that in one case the images are like here, and in one case they're like here. Is that the difference, or
exactly.
I'm not?
It's like the same local structure, but very far apart in the Euclidean space that you start with, which is, I'm presuming, just pixels and colors, right? So a CNN would take care of that. I don't think UMAP would.
Oh, I think we've lost Mihaela again. But, just to meditate on what you've said, that this is what CNNs gave us, that you have this sliding flashlight that goes over the image. And in a way, it's a form of data augmentation, because what you're doing is you're taking one image and you're blowing it up into thousands of images. And because you're sharing the parameters over the entire input space, you're learning that there's a circle up here and you're learning there's a circle down there, and you're regularizing because you're just learning the same parameters on this same thing. But I think Mihaela was saying that because it's this kind of topological approach, even if it finds the pattern somewhere else in the image, perhaps somehow it still finds the manifold in the local vicinity, even though, do you know what I mean?
That's the part I'm just not getting that from the formula, because it really looks like clustering, essentially, with some, entropy thrown in there.
Yeah. Yeah, because on the activation alias paper, I mean, I've not read it in any detail, but by the sounds of it, it's using a CNN encoder and then doing UMAP on the output activation. So the implication seems to be that CNNs give us what we need to do computer vision, just mostly because of this parameter efficiency and this regularization from sliding this window.
There was a really good talk in ICML this year talking about how underpinning all of this is all nearest neighbor algorithms, like convolutional networks are nearest neighbor, manifolds are nearest neighbor. And so just talking about the theoretical underpinnings of all this is nearest neighbor approaches. So I don't know if you guys have used before, like force-directed networks are very similar to UMAP. Yeah, so there used to be a whole bunch of JavaScript libraries that you could use to do force-directed graph layout, right? So if you're trying to show 500 nodes or something like that, how do you lay them out? And UMAP is very similar to those approaches.
Yeah, but force-directed graph algorithms are really slow, aren't they?
Yeah.
Because they're quadratic.
Yep.
But presumably you could do something similar with this, local sensitive hashing. So you could use approximate neighbor search to improve the performance of the force-directed graph algorithm.
Yeah, I mean, what's cool with the UMAP on top of CNN idea is you could allow the output dimensionality of the CNN network to be much higher than you ordinarily would, because then you're relying on this UMAP procedure to reduce the dimensionality to something reasonable.
Yeah, absolutely.
So while she's still gone, do either of you happen to know, I'm really curious what this notion of UMAP preserving more of the global distance means, because I mean, in any projection, when you reduce the dimensionality, you can't preserve all distances. So by what measure are they saying that UMAP is more preserving than t-SNE?
Well, I think Mihaela at the beginning was talking about this objective function, so that there's the original, I think it does a spectral projection, and then it does this iterative optimization problem, which finds the best placement of the points. And she was saying that in UMAP, it moves to this new formulation, which uses the cross entropy. And the two terms in that function were sort of, one was the clumps and one was the local relationships. And it kind of balances those two things.
Oh, okay. So it's just attempting to balance the two distance metrics, but it's still not preserving of distances. It just has at least some balance.
Yeah.
The problem with t-SNE is that it does do the clustering well, but what happens is things that are fairly far apart in terms of their representational distance can be put together. So Mihaela was showing how the sneakers, boots, sandals area was very close to the shirts or something like that in the t-SNE, whereas in UMAP it is fairly far apart, which is what we're looking for.
Hi everyone, sorry again. I'm back.
Hey Mihaela, no problem at all.
Yeah, I'm so sorry about that.
If you weren't leaving Microsoft, we'd petition to get you a new computer, but
yeah, it just has some issues charging, unfortunately. Yeah, I'll be finding the right slide and I'll jump back in 1 second. Okay.
No problem.
So now, okay, perfect. Let me know when you can see.
Just coming up. We've been having another philosophical digressions. I'm so glad that we've got Keith back because he's just been on vacation, and you can always rely on Keith to drive the philosophical discussions. It's brilliant.
for better or worse.
All right, cool. All right, so in the last half an hour, I don't know how much time we'll have to actually go into the topological mathematical arguments, but at least I want to get sort of the computational, go a bit deeper into the algorithm. Maybe we'll actually answer a lot of our questions. So first, let's look at the graph construction. And our goal is to construct a directed weighted graph from the high dimensional representation of the data. So for every point, so here in the algorithm, for every point xi in the original space, we're finding their k nearest neighbors using approximate nearest neighbors algorithm. Then we are finding the rho I, which is the distance to the closest nearest neighbor, and then we define the edge weight on the graph as being the exponential of the. I missed another minus sign here. The negative of the distance that's farther away from the closest neighbor. So anything that's closer than the closest neighbor would be assigned a weight of 0. Sorry, a weight of 1, because exponential of 0 would be 1. And sigma I is so what this results, it means that the edge weight to the nearest neighbor is 1, and then from then the edge weights in the graph decrease exponentially. Sigma I is a normalizing constant. We find this via binary search, and the goal is for this this A of xi, xij represent all the weights that go from the node I. So we want the sum, essentially what we want is we want to normalize the sum of the weights that come out of a node. So we want to normalize it such that it's something that scales with the number of neighbors. And by experimental experiments, the authors found that log 2 of k produces some has some nice properties that we're not going to go too much in depth right now. So what we're talking here is that beyond the first neighbor, we are going to have exponential decay in the weights on the graph. What this sort of induces is a hockey stick distance metric. So this is metric that essentially we're saying the distance between points are virtually 0 if points are closer than the nearest neighbor, and from that point on they scale. They're scaled by that sigma I that we've defined earlier. So the alpha here on the the angle that this distance metric makes depends on sigma. So sigma would be a large value if let's say the neighbors are really far away, to sort of normalize these distances. Yeah.
Last week we were having a conversation about this, and you said there's some relationship with the kind of sparse grouping you get with the curse of dimensionality. So as the number of dimensions goes up, you have this kind of sparsity property. Is it related to this?
It is. I was going to explain this later, but I don't know if we'll have time, so maybe we should just actually go into it right now. Okay, so there is this. Can you see this? Or oh, sorry.
I can see the two graphs.
No, it's a new graph that I'm trying to present, but it's not stuck here. Sorry. So I can't. Oh, oops. So sorry.
Does that say Google? Did that say Google?
Sorry. My fault. Yeah. So what this is saying essentially is that when we look at if we just sample a bunch of random points uniformly at random in different dimensions. So if we sample we range from a 2-dimensional sort of hypercube to a 128-dimensional hypercube, we can see that in high dimensions the distances fly to the left, which is expected. But then when we normalize these distances in high dimensions, what we can see is that they get scooshed and smooshed towards one point. Essentially, what it means that all the distances in high dimensional space look the same. In high dimension, the first neighbor is sort of pretty far because you have only, let's say, 100 points, and you have to fit them. You have 128-dimensional space to move around, and then all the other neighbors are virtually indistinguishable for the first. So in practice, if we were to use that, it would lead us to a lot of weights in that graph that are very, very small. So it wouldn't really be able to distinguish between the first neighbor and the subsequent neighbors. So if we sort of create this hockey stick distance metric in which we count the distances only starting at the first neighbor, we can this here. I don't know where I had this. I knew I had something. Well, okay, it's probably not here. So essentially, if we were to normalize to set as 0 the distances that are before nearest neighbors, we create this this normalized distance that has a nicer distribution. So essentially, we're only counting for every subsequent neighbor is not how far it's for the original point, but how far it is from the first neighbor. So the idea is to distinguish between the first neighbor and the subsequent neighbors. So that's why, well, that's kind of an intuition for why we have that hockey stick. So let's go back. In the graph construction, we have this symmetrization step. So we have the adjacency matrix for the directed graph, and we want to compute a symmetric matrix by taking this is called the T conorm product of a matrix. And essentially, if you are to look at element-wise, it's exactly what we were describing earlier. It's taking the sort of the weight from J to I. So this new entry becomes the weight from J to I plus the weight from I to J minus the product of their weights, and that's how we go from a directed graph to an undirected weighted graph. And once we have this matrix, the next step is to embed this matrix in a lower dimensional space. So first is how do we initialize? How we take this graph and initialize it into a 2D or 3D or 7D space. So as an initialization step, UMAP uses spectral embedding to get sort of a first layout. So given a weighted adjacency matrix, and we construct D, the degree matrix for the graph. So D is just a diagonal matrix that on every element of the diagonal has the number of edges that come out of that vertex. We construct the symmetrized Laplacian, which is a well-known matrix corresponding to a vector. Intuitively, this matrix L, so what it looks like, it's a symmetric, it's a positive semi-definite matrix. On the diagonal, it has ones, and off diagonal, it has the negative of the edge weight scaled by the degree of the vertices on either side. So what this sort of means is if you have in absolute value, if you have a large number, means that weight is very meaningful for these two vertices, particularly because if they have sort of less like fewer things coming out of them. Whereas if two vertices have, they're very popular, they have a lot of edges coming out of them, then that sort of weight between the two decreases its importance. So when we compute the eigenvectors of L, we get something known as the spectral embedding of a graph, which preserves some very important properties of the graph, such as connected components, traveling distances on the graph. So I guess it suffices to say that it produces a 2D or whatever lower dimensional embedding that preserves some properties of the graph. And since the graph was designed to encode properties of the high dimensional space, this spectral embedding is a good way to sort of start the layout of the graph in lower dimensional space from a really good starting point. Okay, so then we're talking about the how we optimize this embedding. So we want to minimize the cross entropy between the membership strength in the graph and the membership strength in the lower dimensional embedding. So when we look at this cross entropy formula, we have two terms, one that looks very much like t-SNE, the one on the left, and one that's different, and this can be interpreted as getting sort of the cluster tighter together, and this one is interpreted as if something is very different in original space. If this is a large value, then we want this to be a large value as well. So we want to separate sort of the gaps between to increase the gaps between points that are very different in the original space, which is why UMAP sort of ends up with a much more sort of pulled apart cluster structure. So when we sort of take this apart, it has two terms. So the logarithm of a fraction is the difference of the logarithm. So when we do this transformation, this optimization does not depend on mu a, because mu a is a function of the original space. So we've learned those edge weights already. So the minimization only happens with respect to nu, which is the membership strength in the lower dimensional embedded space. So how we define this mu a? So mu a, we already talked about this. It's essentially is distributed to. So it's very similar to the T distribution used by t-SNE, except that there's the constant C1 here. C1 here and C2 here. And the reason we have the C1 and C2s is because we want to fit C1s and C2 such that we approximate the wave decay structure that we have. So if you remember, in the original space, we had this thing in which up to the nearest neighbor, the weight was 1, and the weight started decaying later on. We want to do here kind of have a similar structure. However, we want to use an optimization-based approach. We want to use gradient-based optimization. If we use directly this sort of hockey stick, this kinky membership strength function, then we're not going to be able to differentiate. So we were trying, essentially, we're using this formulation as a way to find a differentiable approximation. So we just want to mimic the same weight decay that the graph has. And here we have a hyperparameter called the minimum distance. So essentially, if 2 points are less than this minimum distance in the embedded space, we're going to give them weight of 1 or membership strength of 1 in the embedded space. And we're going to start sort of decaying exponentially from that point on. This min distance is a hyperparameter. Essentially, it maps the distance between nearest neighbors in high dimensional space to low dimensional space. Essentially, what you're saying is, if 2 points are nearest neighbor in high dimensional space, I want them to be about min dist apart in embedded space, such that so essentially what this achieves is that all points that are nearest neighbor, so in one area of the graph, you might have sort of nearest neighbors that are really close by, because there's like the data is very clumpy in that area. So this would be so the distance between nearest neighbors would be smaller, whereas another area of the graph you might have sort of a larger variation, so the distance between nearest neighbors might be larger, and this essentially makes sure that all nearest neighbors in the embedded in the embedded space are about min dist away. This really helps with visualization.
Yeah, that isn't largely handled by that sigma parameter that was calculated earlier. Why? What happened with that?
So the sigma parameter, yeah, that's actually it's intended to normalize the membership strength in the high dimensional space. This would work. Having a min dist of 0 would work. However, it is generally an aesthetic parameter because as we try to sort of optimize for this cross entropy, what the visualization would do, it will put, if 2 points are nearest neighbor, it will put them like right on top of each other, making sort of visualization very hard to view because if you put 2 points that are nearest neighbor on top of each other, you're going to optimize the cost metric. So you're going to essentially, improve your cross entropy. So in order to avoid this like over plotting on top of each other, we say it's okay if you don't put it on top of each other. If you are min dist away, it's fine enough. Don't try to move them even closer. That's kind of what it says.
Okay.
From an aesthetic point of view. And it's also nice because it has this interpretation of following the weight decay property that the original embedding had from high dimensional space to graph. Okay. So in terms of the algorithm, how we actually optimize is a sampling-based gradient optimization. So we have those two terms of the cross entropy. One is attractive and one is repulsive. So we want to apply attractive force along the edges proportional to the edge weight, and we want to apply repulsive force along the vertices. So for a certain number of epochs, essentially we sample an edge with an edge A with probability mu of A, which is the strength of that edge weight in the graph, and we move in the direction of the gradient of mu of A. So that's sort of the attractive force. And then we cannot sort of directly sample negative force. So one approach would be to just, take all the vertices and move all of them away from, so take all the other n-1 vertices and move them away from this one that we're looking at right now. But this would be computationally infeasible. So we take sort of a negative sampling approach in which we sample just a certain number of vertices from the graph, and for those vertices we move them we move that vertex sort of in the opposite direction, like applying the repulsive force. So this the alpha is the learning rate, and you can schedule sort of different learning rates and do it for a certain number of epochs, and then you start so this first starting off with the spectral embedding and then doing this for a number of epochs, you achieve the final embedding. So we're talking about these two hyperparameters, the k, number of neighbors, and min dist. So number of neighbors can be thought of as the size of the local neighborhood. It's a parameter that trades off between fidelity to small scale structure and fidelity to larger scale structure. So with smaller k values or number of neighbors values, points tend to be broken into a lot of sort of small connected components, as you can see here, for a small number of neighbors. With larger values of k, we might lose sort of local structure in favor of sort of uncovering sort of larger neighborhoods. In contrast, min dist, already talked a bit about it, is mostly a aesthetic hyperparameter affecting the output. So when the min dist is small, sort of points that are nearest neighbors in the original space kind of get bunched up together here, whereas here, when the min dist parameter increases, it sort of pushes points farther away, such that it wouldn't create overplotting. I guess the caveat with MinDist is sometimes if this parameter is too large, it can sort of mask away the clustering behavior because it pushes the points too far away in the projected space.
Could I ask a quick question about, on the previous slide, you were talking about the learning rate, and there's loads and loads of stuff in the optimization literature about learning rate scheduling, learning rate annealing, warm restarts, and so on. And, would it be a good thing to do to change the learning rate? How does it affect the stability and the robustness?
So the learning rate uses a very, very simple schedule in which at every epoch, the learning rate decreases a bit. So it's nothing too fancy. I think that's definitely an area which it could be interesting to see how a different learning rate would help. And I don't know if they've done experiments and trying different schedules for learning rates and how it affects the output, but I think it would be a pretty easy change to implement and experiment with. And definitely an area of future improvement. Yeah, but I'm not sure how it would affect it. They're arguing that their projections are very stable, so I'm assuming that it wouldn't affect it too much. But that's
it might just there could be some work there to make it converge quicker, or better anytime performance.
Like it could have definitely better performance if it converges better. So, for example, like they're arguing the biggest sort of performance improvement is the fact that they start off with a really good embedding to begin with, that spectral embedding that uncovers some really interesting properties of the graph, and then they just optimize from there, as opposed to starting off with like just random points in a lower dimensional space and then optimizing from that perspective.
Cool.
Yeah, really good question. Okay, so from an implementation point of view, we have this algorithm for finding approximate nearest neighbors, which is based on random projection trees and nearest neighbor descent. We already talked about that. It's really fast. It's being used as subroutine, so just assuming that it has a good performance. For the graph layout, we are using spectral embedding of initialization, and then as optimization, we use stochastic gradient descent and negative sampling to iteratively improve the layout. In terms of code, all the code is written in Numba. It's really easy to read. Very, very user-friendly. To improve computation, it uses Numba, which is a just-in-time compiler to an LLVM. It's very, very easy to use. It just has essentially a decorator on top of the function that makes all the magic to work really fast in terms of computations. Certainly, this could be optimized. This could be run sort of distributed and with on C++, and there's definitely room for improvement, but just with that, the fact that just by using sort of very high level code and just using the Numba GIT, it's able to overperform like highly optimized t-SNE implementations. Okay, so I don't know how much time do we have? I have about 5 minutes. I think there's definitely not enough time to go over the mathematical foundations, but let me just for the sake of I guess entertainment, read how like the algorithm is described in the paper and see how like kind of I guess unless you come from a topological or algebraic geometry background, it would be very, very hard to like wrap your head around it. So what they're saying is that at a high level, UMAP uses local manifold approximations and patches together their local fuzzy simplicial set representation to construct a topological representation of the high dimensional data. I'm like, what is this stuff? So this is why I decided not to explain the algorithm from a like topological foundation and start from more of a computational and t-SNE comparison. But this actually makes a lot of sense. And what is really, I'm definitely not doing justice to this paper because what is really cool is that all the algorithmic decisions behind why neighborhood graphs make sense, why use the skin key decay function, why symmetrize the adjacency matrix are actually motivated in very, very, very well established mathematical theory. So as a primer, for now, I assume that topology is just the study of geometrical properties of objects. This is very, hope no topologists are listening to me right now. Manifolds, what are manifolds? So manifold, the special type of a topological object that sort of is smooth and nice. So for example, lines and circles are manifolds, but like figure eights are not manifolds because they self-intersect, or like a sphere and a torus is a manifold, but a Klein bottle, which is this thing on the top, it's not a manifold. Okay, and a Riemannian manifold is like a different species of manifold that has a nice extra property that it's equipped with an inner product, which means that it sort of admits well-defined notions of distance. So essentially, it's just a manifold with a measuring stick. Nothing too complicated. What is manifold learning? So this assumption that data lies on the natural data lies on some sort of structure, and often we assume that the manifold dimension is much lower than the ambient dimension. What does this mean? So, for example, if you think of MNIST, it's like 784 dimensions. You don't need 708-dimensional space to represent like 10 digits. Most likely there is some sort of like topological representation, like maybe like all those images sort of form this really nice, I don't know, blob in space or some other shape in space that is a manifold. And the goal is to learn this manifold directly from data. So the goal is to identify a graph structure that reflects the topology of the data. So here, as you can guess, the topology is very simple. It's a sine wave, but topologically, this is equivalent to just a line because you can stretch it on both sides and just get a line. So assume you have a line in a high-dimensional space. So that's our topology. So we're trying to identify a graph structure that reflects the topology of the data. Sorry, let me just 1 second.
Yeah, Mahela, don't feel that you need to rush because we're going to put this on the YouTube channel anyway. So if people need to drop off, that's fine. But just take your time.
Yeah, just give me 1 second. I'm running into a small technical issue, and I am back. Okay, yeah. So the goal, as I said earlier, we have this manifold. It's a line in a high dimension, and the goal is to identify a structure that reflects this topology. So there's this nerve theorem that essentially tells us that we can approximate a high-dimensional manifold via this sort of Lego boxes that are called simplices. So a 0 simplex is just a point, a 1 simplex is an edge, a 2 simplex is a surface, a triangle, a 3 simplex is a tetrahedron. So essentially what we can do, we can take this simplices and glue them together into simplicial complex, such that as we glue them together, we essentially recover most of the structure of the manifold. So if you imagine we have a set of points that are that topologically form a torus, we can approximate this torus by kind of Lego blocks of these simplices. So something in the simplicial geometry that's known as a zero skeleton is just the vertices of this. So a simplicial complex is essentially just a extension of a graph. So if you take just the zero skeleton, which is the vertices, and the 1 skeleton, which are the edges, you just get the regular graph that we know very well. If you were to take 2 skeletons, then you're going to take, graphs with, surfaces. So it's kind of a graph on steroids. If you were to take up to 2 skeletons, you would have sort of graphs with surfaces and little tetrahedrons that would fill up the volume. So you have a kind of a more and more complex definition of a graph. But essentially, if we just take the 0 and the 1 skeleton, we get, our well-known graph structure. So this kind of motivates why building a graph to approximate a manifold is actually a pretty sensible decision. So now we want to construct a graph such that it reflects the topology of the data. So what this our nerve theorem earlier was telling us that essentially if we build covers around every point of interest, and we say that there's a nerve between 2 vertices if those covers intersect, then that kind of nerve union of all of them is able to recover most of the interesting properties of the topological space. So what we're doing here is exactly the same. We have our point, we build a cover, which is essentially a unit ball around every point, and we say, okay, if they're intersecting, we're going to build a graph. Okay, what is the problem? The problem is that this is creates a lot of like disconnected components, and while it uncovers some of the properties of the original line, it fails to see that it's a continuous line, and it breaks it into many components. The problem with this is that this theorem only works when there's an assumption that the data is uniformly distributed on this manifold. So if the data was kind of very nicely spread out across this sine wave, then this would work perfectly. We have our covers, they all intersect nicely. We can just build a graph that's like essentially one line from beginning to end, and we're great. We just uncovered all of our manifolds. But when is data, uniformly distributed on anything? So what we have to do is essentially not change the data or change our but change our understanding or the way we look at it. So what we want to do is imagine this like manifold space, and we want to contract it and expand it in such ways such that the data looks uniform. What this means in practice is that we vary our notion of what a unit ball means in different areas of the manifold. So in an area that has a low density of points, a one-dimensional ball might be something like very huge to accommodate the fact that it's a low density area. While in a high density area, a unit ball might be something very small. What this achieves is essentially every point will define a separate metric space, such that every point will have its own sort of local cover. And it's designed in such a way to have the same number of points. So this should probably ring a bell by now. If it has the same number of points, it has the same number of the closest points, which is exactly the case as the K-neighborhood graph. What this does is when we build this cover of varying sizes, we're essentially assuming that this is the neighborhood of the point on the manifold. Essentially, remember we were talking about what a manifold is something, a topological object that can be approximated as a straight surface when we zoom in. This is kind of like the size of our magnifying glass. We assume that within the cover, within this unit ball norm, for example, we have it here, the manifold is essentially flat. So let's say if we were to have a ball that was actually much bigger here, we might lose some of the interesting, maybe here's like another kink or something, we might lose it because it's sort of like all smooshed out in this cover. Okay, so we build a graph based on the intersection of the covers. However, we run into a problem. As we define different metric spaces for each point, we run into incompatible metric spaces. And like we have this Riemannian manifold that's supposed to have a metric space across the whole thing that varies nicely. And now we have a problem because at the intersection of those covers, we don't really know, so if you put a point here somewhere in the middle of the intersection of two covers, let's say like, I don't know, like here, he like that point wouldn't be able to understand what distance means for him or for her, because there's incompatible notions coming from different points around on the manifold. So without going into too much detail, there's a way to fix this, and we fix this by introducing fuzzy simplicial sets. So with the fuzzy set is just like a regular set, except that it's not like irregular sets. You're either part of the set or you're not part of the set. In fuzzy set, you have a membership strength between 0 and 1. So what happens in practice is that every point is defined. For every point, we define a fuzzy set consisting of its k neighbors. And here we see that there's a sort of a weight decay such that the neighbors that are farther away have a lower membership strength. Okay, this leads to a bidirectional graph. And from this fuzzy set theory, it's the only way we can construct fuzzy sets such that we can merge these incompatible metric spaces on the manifold is to give them this the strength that's the negative of the exponential, which motivates our, the way we've defined the edges in the graph. Okay, this seems all fine and dandy. However, there's another thing to do. We have to normalize because it's still, we look at 2 points. We have the distance metric according to point I, distance metric according to point. If you look here, point I, this metric according to point J, and they're still different. So we have to resolve this difference. So here, this is where this normalization came through. This T-norm, T-conorm is a property of fuzzy sets. It's a way to merge fuzzy sets together it's a way to do what's known as a fuzzy set union. Essentially, this is the step that takes all the incompatible metric spaces and smooshes them into one. And it's nice because it motivates this need for symmetrization. It induces a smooth varying distance metric for every point of the manifold, which means that we've done what we said we will do. We've actually learned a metric, distance metric that varies across all the points, so we can embed not only points that are in the graph, but points that lie anywhere in the manifold. And it's nice because we've already talked about this probabilistic intuition that it agrees with. Okay, here we already talked about this, but if we were to do just what I said, this would induce this curse of dimensionality. Okay, so another assumption we need to make is that of local connectivity. As I said earlier, the goal is to distinguish between the first and the next k-1 neighbors. So what are the assumptions from a manifold perspective is that we make the assumption the manifold is locally connected. There's no isolated points. What this creates essentially is a membership strength that decays beyond the first neighbor. The nice thing is the math still works out because we still have a continuous distance function that we've defined here, and when taking the exponential of it, we have a decay function. So and the ability to take fuzzy unions over fuzzy sets doesn't depend on the way the distance metric is defined. So just trust me, math still works. Okay, so what this does, this is sort of explain this necessity for local connectivity that's derived from the curse of dimensionality, explains why there was this decision that was made to have this kind of kinky decay weight function that starts at 1 and then only then decides to decay. Okay. So this is like the graph I was looking for. So having this local connectivity essentially means that when we normalize distances to nearest neighbors, they have again a nice distribution. So it's no longer just one value. Okay, so we're kind of solving the curse of dimensionality. Second part of the algorithm, the graph embedding. Essentially, what we want to do is we took this data in high dimensional space. We transformed it into this fuzzy simplicial structure that's probabilistic and looks like a graph. So we did this to approximate the manifold. Now we want to take this this approximation as a fuzzy simplicial set and map it back to a different manifold. However, this time we're lucky because we know what the manifold is. It's just a simple Euclidean space of lower dimension. What's even nicer is that we don't have to learn the distance metric for every point in the manifold. We already have a distance metric that's constant across everything. So this is the distance metric we were talking about earlier, is the one that approximates this the same behavior. So we want the blue line describes how the weight decay happens in the topological space, which is the strength of the membership and this fuzzy set. So when we embed the graph in 2D, we induce a graph to it, just literally from the distances on in a lower dimensional space, and we want that based on those distances we we build this blue line, which is the strength of membership, and then we approximate it with a differentiable approximation, and then it sort of makes sense. And what the final product is that we have we want to embed the points in the target manifold, which is the lower dimensional Euclidean space, by minimizing the cross entropy between the two simplicial sets. So no longer we talk about just probabilistic terms, but we are more we have a sort of better theoretical foundation. We're not just trying to sort of maximize probabilities. We're actually trying to optimize for the cross entropy between these two fuzzy simplicial sets, because fuzzy simplicial sets are a way to approximate topology. Okay, so one of the theoretical foundations, like a TLDR on what is this algorithm based on. So it makes this assumption that data is uniformly distributed on the Riemannian space. There is a Riemannian metric that is locally constant. The Riemannian metric can be learned from the data, and the manifold is locally connected, and we can model the manifold with this fuzzy topological structure. Okay, so we can express UMAP as a classic manifold learning algorithm that starts with a high dimensional space, then goes on and encodes the topological structure and the local distances via simplicial complexes, which are those Lego blocks that we glue together. Then we merge those inconsistent metric views that each node has on the graph by introducing these fuzzy notions of weight decay. Then we're going to take this fuzzy set representation of the graph, embed this topological structure into an Euclidean space. And then once we do that, we optimize an embedding to preserve distance structure that the original topological space came with. And that's it. Manifold learning. Thank you.
Amazing.
Yeah, that's sorry. I just breezed through that so quickly. I'm so sorry. I hope none of the authors will ever see this, because I definitely butchered the amazingness of the research.
Oh, they will see it. Don't worry.
Right.
No, seriously, Mihaela, this has been absolutely amazing. It's been an epic marathon, and I've learned so much from this. For the folks still on the call, do you have any questions? Not even Keith.
Well, I was just waiting because I don't want to take up all the time. So, yeah, I mean, I'm really curious about their decision to kind of minimize cross entropy as opposed to KL divergence. Why? I mean, what was the theoretical justification for that? And what would happen if I did exactly the same thing as this algorithm, except I minimized KL divergence?
Okay, so the reason, I think maybe there's a two-part answer to this. So first, the reason why the cross entropy makes more sense is that when you think from a topological perspective, you have this two fuzzy set representations, one in the original high dimensional space and one in the lower dimensional space. And they're not really viewed as probability. There's a probabilistic intuition behind it, but they're not viewed as probabilities. So in that sense, cross entropy makes a lot more sense. Practically, having the term on the right helps with pulling away, explicitly helps inducing this negative repulsive force on edges that correspond to points that are very far away in original space. So I think practically it has that that behavior of that's the only place from where UMAP gets to claim that it has some sort of global structure. So I think if we were to take this away, I believe the results might be a lot more similar to what t-SNE outputs. But I think it would be an interesting comparison to see sort of to how much the output of UMAP is credited to the term on the right versus the weights of the graph are computed.
Right, because I mean that term on the left is KL divergence, right? Or it's the same form.
Yeah, it's the KL divergence of the if you were to think of it from a probability distribution of essentially the negative of that event, of those events, yeah.
Yeah. Okay. And then, so go ahead.
But I guess that the reason t-SNE doesn't use this KL divergence is because this optimizing for this negative term is a bit harder, which is why you can't just sample and update. You have to, so for every edge you can just sample and update. You have to sort of sample all the other edges and then update the edge that you're on currently. So it's a bit more complicated. So okay. I guess maybe that's the reason why they didn't do cross entropy and they did KL divergent, because it's easier to optimize. And I think from a probabilistic perspective, that's kind of an optimal transport notion of how you take one probability to a different probability.
I think her network's just lagging, right? Or is it mine?
Yeah, I think it's Mahela's. It's just.
Sorry, where did I get? Sorry, where did you lose me?
Right after you talked about the transport of probability.
Oh yeah. That's almost the end. Yeah, essentially, like there's an optimal transport notion of moving sort of one probability to a different probability, and the way to do it optimally is to minimize the KL divergence. So I think from a probabilistic point of view, it's a natural thing to optimize for.
Okay. And so the only properties of a manifold that they appear to be using throughout the entire paper is just local approximation by simplices, right?
Yes, and the assumption that locally the data within the cover can be thought as a flat surface.
Right, and so just that, along with the assumption that these distance metrics are useful. They have some meaning, right?
Exactly. So I guess it starts with the fact that if you have a manifold in which the data is uniformly distributed, then by using this NER theorem and building this unit ball covers, and which leads to this simplex complex, then this theorem sort of says that the simplex approximates well a topology of the original data. And then that's kind of the genesis of the algorithm or the idea. We can approximate uniform data by simplices, but then our data is not uniform. How do we make it uniform? We make it uniform by changing our notion of distances on manifolds in different places. So in some places we use a magnifying glass, in other places we zoom out, and we have sort of different distance metrics. And the fact that you can have different distance metrics defined on manifolds is something that there's a lot of theory about. And like this image that I showed earlier of merging together incompatible metric space is sort of a textbook image of like metric learning on manifolds.
Okay. All right, I'm going to pause here, but I have more questions later.
Yeah, please reach out. Yes, for sure.
No, I mean, I'm going to pause for.
Okay.
Or I continue to hog the time.
Other folks on the calls, any questions?
Also, I want to be mindful of people's time. Already this went a bit over time, so yeah, no worries if you decide to take off.
Looks like I'm going to have to jump in again, Tim.
Go for it, Keith. Okay,
so, I mean, maybe this is obvious, but so this is a very local method, right? I mean, they say that they kind of, maybe we preserve some global distance a little bit better than t-SNE, but at the end of the day, it's really a local method, right? And so I'm just really curious about the current state of the literature. So if we consider this, say, the state of the art or one of the state of the arts for local methods, what's the current state of the art for global structure determination?
I think that question is a bit more domain specific. So I guess the bread and butter of it is PCA. It's very well established. But
I'm sorry. Let me rephrase. For nonlinear global determination.
Oh, nonlinear. Oh, there's no such thing. I don't think there is at least not to my knowledge.
Okay. So that's going to be your thesis work then, right?
We'll see. Most nonlinear maps are concerned with uncovering local patterns, not necessarily global ones. Because I think it might be hard to even design such an algorithm, because when you're looking for global structure, you inherently want to preserve interpretability. And as soon as you start getting yourself into nonlinear maps, you lose that that ease of interpreting the output.
Which is what we spoke about earlier.
But I'm sure there is something. I don't think it's a lost cause. I'm sure there's maybe something that would be able to identify larger structure while being nonlinear and still having some degree of interpretation.
Well, I mean, so on the slightly more philosophical side, would you say that the human mind is sort of very good at finding nonlinear global structure? Is that a fair statement?
I mean, I guess to go into philosophical debates, I guess talking about what the.
I mean, that's one of the things that we believe that we're very good at as compared to algorithms, I guess I should say.
Yeah, I think that's fair.
So ultimately, we'd like to find out some more algorithmic ways to do that. So,
well, yeah, I think that's fair to say, but I wouldn't be fair to ask of an algorithm that does dimensionality reduction to do those things, because first of all, as humans, we have a lot of context and background knowledge and experience that it's not something like UMAP does not have access to. So if we were to humanly look at the points as numbers, we wouldn't be able to uncover any structural patterns.
Sure, I mean, totally agree. I mean, but on the other hand, all's fair in sort of algorithmic development. So even if it was some nonlinear global structure determination that took advantage of a bunch of prior knowledge, kernels or whatever, I mean, that's still interesting. I'm just curious what the state
I think that's definitely interesting. And I think it's actually, there's a lot of research going into this, I guess, more generally under under two umbrellas. So there's a general umbrella for representation learning, which are trying to learn sort of good representations. And that's a very active area of research. And I guess another area that's related to this is, the one-shot or zero-shot learning, in which you're sort of building up this. It's very similar. It's very much related to representation learning, in which you're sort of building this understandings of data and as it comes, and you're trying to. I guess in a sequential fashion, improve the way you understand a certain domain and stuff like that. But I think what's true about those fields is in many ways they're very sort of not well defined, and they're very fuzzy, to borrow a pun from here. Whereas this approach is not really attempting to be sort of a general AI algorithm. It's it's designed for a very specific purpose, and it's mindful of its own limitations.
Gotcha. Thank you. That makes sense.
Cool. Okay, folks, I'm going to draw this call to a close. This has been absolutely amazing. Mahela, thank you so much. The amount of preparation that must have gone onto this is breathtaking. I'm incredibly excited to get this on the channel, because I know this is going to be really, really popular. But anyway, thank you so much. I know that this is pretty much your last day at Microsoft, so it's been amazing having you here, and I very much hope that after you've graduated with a PhD from Berkeley, you come back and join us.
Thank you so much. Thank you for your time, and thank you for making Microsoft such an awesome experience. And sorry for all the technical problems.
No problem at all. It's been amazing. I think it's been one of the very best paper calls that we've had. Thank you so much.